Out there, in the dark and frigid reaches of our solar system, beyond the orbit of Neptune, drifts a world that defies explanation: Varuna. This distant Kuiper Belt object, named after the ancient Hindu deity of the cosmic waters, holds secrets that have puzzled astronomers since its discovery in the year 2000. Imagine a place so far from the sun that sunlight is nothing more than a faint, flickering star, where temperatures plunge to hundreds of degrees below zero, and yet, somehow, this frozen relic whispers clues about the birth of our solar system. Varuna isn't just another icy rock in the void. It's a cosmic enigma, a puzzle wrapped in layers of ice and mystery, and today we're diving deep into the 25 most baffling questions that surround it. What makes Varuna so extraordinary? For starters, it's one of the largest known objects in the Kuiper Belt, a ring of icy bodies left over from the solar system's formation. But size is just the beginning. Varuna's shape, its bizarre rotation, and even its surface composition defy expectations. Some scientists believe it might be a relic from a time when the planets were still taking shape, a frozen time capsule holding stories from 4.5 billion years ago. Others speculate it could harbor surprises that challenge everything we think we know about the outer solar system. And then there are the whispers of something even stranger. Could Varuna's mysteries hint at forces or phenomena we've yet to discover? This isn't just a story about a distant world. It's a journey into the unknown, a chance to explore the edges of human understanding. Every unexplained detail about Varuna, from its unusual brightness variations to the way it spins like a top, invites us to question, to wonder, and to imagine. What if this icy wanderer holds the key to unlocking secrets about our cosmic neighborhood? What if its puzzles force us to rewrite the textbooks? Buckle up, because we're about to unravel 25 of the most intriguing mysteries of Varuna, and by the end, you might just see our solar system in a whole new light. The deeper we go, the stranger it gets, and that's where things get truly fascinating. The first mystery surrounding Varuna is its bizarre rotation speed, spinning so fast it defies all expectations. For an object of its size, roughly half the diameter of Pluto, you'd expect a slow, stately rotation, perhaps taking days to complete a single turn. Yet Varuna whirls at a breakneck pace, finishing a full rotation in just under 6 hours. To put that into perspective, Earth takes 24 hours to spin once, and even Pluto, another Kuiper Belt heavyweight, rotates at a leisurely 6.5 days. Varuna's speed is so unusual that it immediately raises questions: what could possibly be driving this cosmic sprint? One leading theory points to violent collisions in the distant past. Imagine two massive ice worlds smashing together in the chaotic early solar system, the impact sending Varuna tumbling like a struck top. If a sizable object struck it just right, the force could have revved up its spin to the dizzying speeds we see today. But here's the catch: most collisions in space tend to be messy, often leaving debris or altering orbits in noticeable ways. Yet Varuna's orbit remains stable, and we've yet to spot any obvious remnants of such a catastrophic event. This raises doubts: was it truly a collision, or could something else be at work? Another possibility lies beneath the surface, literally. Some scientists suggest Varuna's internal structure might play a role. If its core is denser than expected, or if pockets of volatile ices lurk beneath the crust, shifts in mass could have accelerated its spin over time. Think of an ice skater pulling their arms in to spin faster. Small changes in how weight is distributed can dramatically affect rotation, but even this idea has holes. Current models of Kuiper Belt objects struggle to explain how such a large body could maintain this kind of speed without breaking apart. Then there's the wild card: forces we don't yet understand. Could unseen gravitational tugs from hidden neighbors, or even interactions with dark matter, be nudging Varuna along? It sounds like science fiction, but the outer solar system is full of surprises, and conventional explanations keep falling short. Every time we think we've pinned down the answer, Varuna's relentless spin throws another curveball. What's clear is that this isn't just a quirk, it's a clue. The way Varuna moves could rewrite our understanding of how objects in the Kuiper Belt behave, revealing hidden dynamics from the solar system's earliest days. Until we send a probe to study it up close, this icy speedster will keep spinning its secrets just out of reach. Varuna doesn't just spin like a cosmic top, it also wears a cloak of darkness. While most icy objects in the Kuiper Belt gleam with a frosty brightness, reflecting anywhere from 10 to 70% of sunlight, Varuna barely bounces back 3 to 6%. That makes its surface one of the darkest ever measured in the outer solar system, darker than fresh asphalt on Earth. Why would an object made largely of ice, a material known for its reflectivity, appear so eerily dim? The answer might lie in a cocktail of cosmic chemistry and the relentless wear of deep time. One leading explanation points to ancient organic compounds. Picture this: over billions of years, radiation from distant stars and cosmic rays bombarding Varuna's surface could have transformed simple ices into complex, tar-like substances known as tholins. These dark, carbon-rich molecules are thought to coat many outer solar system objects, including Pluto's moon Charon and the mysterious dwarf planet Makemake. If Varuna's surface is laced with tholins, that could explain its shadowy appearance. But here's the twist: other Kuiper Belt objects with similar exposure to radiation don't always appear this dark. So what makes Varuna different? Some researchers speculate its chemistry might have been altered by unique conditions during its formation, perhaps involving rare mixtures of methane or nitrogen that cooked into darker compounds under the sun's faint but persistent glare. Then there's the role of space weathering. In the airless void of the Kuiper Belt, microscopic impacts from dust and high-energy particles can slowly but surely darken an object's surface, like cosmic sandblasting over eons. The longer an object sits exposed, the more its pristine ice gets ground down into a dull, charcoal-like crust. Varuna, as one of the older inhabitants of the Kuiper Belt, may simply have endured more of this weathering than its neighbors. Yet even this theory has gaps. Some equally ancient objects, like Haumea, retain much brighter surfaces despite similar exposure. That suggests Varuna's darkness isn't just about age, it's about composition and environment working in tandem. A wilder possibility: Varuna's dark patches might hint at active processes still at work. On Saturn's moon Iapetus, bizarre dark material accumulates in ways scientists still don't fully understand, possibly due to interactions with other moons or even volcanic activity. While Varuna almost certainly isn't volcanically active, could it be collecting dark debris from collisions or orbital interactions we haven't yet detected? Or does its spin play a role, flinging lighter materials into space while darker residues cling to its surface? Whatever the cause, Varuna's darkness isn't just a curiosity, it's a window into the forces that shape the solar system's farthest reaches. By studying what blankets its surface, we might uncover secrets about how organic molecules spread through the cosmos, or how the building blocks of planets evolve under extreme conditions. Until a spacecraft finally ventures out to snap close-up images, this shadowy world will keep its secrets tucked away in the deep freeze of the Kuiper Belt. But one thing's certain: in the darkness, there's always more to discover. Varuna's shape is another puzzle that baffles scientists, defying the typical roundness we expect from large cosmic bodies. Most objects in the solar system with enough mass eventually collapse under their own gravity into a spherical form, like planets and large moons. Yet Varuna, despite its size, comparable to mid-sized asteroids or dwarf planets, seems stretched more like a squashed football than a perfect sphere. This irregularity raises eyebrows. How could something so substantial resist the pull of gravity that usually smooths rough edges into a ball? The answer may lie in its surprisingly rapid spin. That dizzying rotation we just discussed, the one that whirls Varuna around in under 6 hours, could be distorting its shape. Think of spinning a water balloon. The faster you turn it, the more it flattens at the poles and bulges at the equator. Now imagine that balloon made of rock and ice, frozen solid but still bending under the forces of motion. This rotational flattening might explain Varuna's stretched appearance, but here's the catch: even accounting for its speed, models suggest it shouldn't be quite this elongated. Other fast-spinning objects like the dwarf planet Haumea show flattening, but Varuna's degree of distortion seems extreme. Then there's the possibility of a violent past. If Varuna was once part of a larger body shattered by a catastrophic collision, its current shape could be a scar from that ancient breakup. The impact might have left it tumbling asymmetrically, with chunks of debris torn away unevenly. Some astronomers point to its dark surface as further evidence. Perhaps that coating isn't just from cosmic weathering, but from the remnants of a catastrophic encounter, like soot after an explosion. Yet, unlike other collision-shaped objects such as the debris-strewn asteroid Pallas, Varuna doesn't orbit amid a cloud of fragments, making this theory harder to prove. Another clue comes from its composition. Most Kuiper Belt objects are loosely packed rubble piles, held together by gravity rather than solid rock. If Varuna's interior is less dense than we assume, perhaps laced with hollow spaces or layers of porous ice, its structure could be more flexible, bending into an oblong shape under stress without fully collapsing into a sphere. Compare it to a snowball squished in your hand versus a ball bearing softer materials deform more easily under pressure. This might mean Varuna isn't just a frozen relic, but an object still settling into its final form, its shape a snapshot of an ongoing process. But the biggest question remains: what does this mean for our understanding of the Kuiper Belt? If large objects like Varuna can stay irregular, it challenges the assumption that gravity always wins, sculpting everything into spheres given enough time. Maybe the outer solar system is stranger than we thought, with forces beyond just gravity shaping these distant worlds. Or perhaps Varuna is a rare survivor of a more chaotic era, its oddity a fossil from a time when collisions and spin ruled the day. Until a spacecraft visits, measurements from Earth can only hint at the truth. Every irregular curve, every shadowed ridge on Varuna's surface could hold secrets about how the solar system's edge evolved, and why some worlds refuse to play by the usual rules. One thing's certain: in the realm of cosmic oddballs, Varuna stands out, not just as a curiosity, but as a challenge to our textbooks, and that's what makes it worth watching. Varuna's silence speaks volumes because, unlike its distant cousin Pluto, which boasts a hazy, thin atmosphere of nitrogen and methane, this icy world seems to have none at all. For an object nearly half Pluto's size, that absence is more than odd, it's a cosmic contradiction. Atmospheres aren't just decorations, they're fingerprints of a world's history, shaped by its chemistry, temperature, and even collisions. So why is Varuna eerily bare when similar Kuiper Belt objects cling to their gaseous shrouds? The answer might lie in a delicate dance between gravity, composition, and the relentless chill of deep space. Start with Pluto's atmosphere, a wispy veil that thickens and thins with the dwarf planet's elliptical orbit. When Pluto swings closer to the Sun, ices on its surface sublimate, transforming directly from solid to gas to briefly replenish its skies. But Varuna's orbit keeps it perpetually farther from the Sun's faint warmth, where temperatures hover near -230 degrees Celsius. At that cold, most gases freeze solid and stay locked in the ice. Even methane, which dances between solid and gas on Pluto, becomes as rigid as rock on Varuna. Without enough heat to kickstart sublimation, any atmosphere would collapse like a deflated balloon. But here's the twist: Varuna might not have always been this barren. Some models suggest it could have briefly hosted a temporary atmosphere early in its life, when radioactive elements in its core decayed and provided just enough warmth to vaporize surface ices. Imagine a flickering halo of gas clinging to Varuna for a few million years before fading into the void as the heat dissipated. The evidence, other Kuiper Belt objects like Makemake, show chemical signatures hinting at past atmospheric loss. If Varuna once shared that fate, its missing atmosphere could be a ghost of a more active youth. Yet another possibility is even simpler. Varuna never had one to begin with. While Pluto's nitrogen-rich surface fuels its atmosphere, Varuna's darker, carbon-coated crust might lack the right ingredients. Tholins, those complex organic molecules staining its surface, don't sublimate easily, meaning they'd stay frozen even if temperatures rose slightly. Without volatile ices like nitrogen or carbon monoxide dominating its composition, Varuna could be eternally airless by default. Compare it to Ceres in the asteroid belt, similarly large but without the right chemistry to sustain an atmosphere. The wild card in this puzzle, impacts. A single massive collision could have blasted away any fledgling atmosphere Varuna once held, scattering its gases into space before they could recover. Pluto survived such violence. Its heart-shaped plane, Sputnik Planitia, is thought to be an impact scar, but Varuna might not have been so lucky. Or perhaps its rapid spin played a role, flinging gas molecules outward faster than gravity could recapture them. Ultimately, Varuna's missing atmosphere isn't just a quirk. It's a clue to the diversity of worlds lurking in the Kuiper Belt. Some cling to their gases, others lose them, and a few, like Varuna, might never have had the chance. This icy enigma forces us to ask, what truly makes an atmosphere stick around? Is it size, chemistry, orbit, or just cosmic luck? Until we send a probe to sniff the empty skies of Varuna, the answer will remain as elusive as the gases it refuses to hold. Varuna's surface is a frozen puzzle box of cosmic ingredients, and cracking it open reveals a recipe unlike anything else in the Kuiper Belt. Spectral data. The unique light signatures bouncing off its surface paint a portrait of water ice mingling with strange hydrocarbons and possibly those enigmatic tholins we've seen elsewhere. But here's what's truly baffling. While many distant objects share some of these components, Varuna's blend is oddly lopsided. It's as if you baked a cake with the same ingredients as your neighbor but ended up with something entirely different, and no one can quite figure out why. Start with the water ice. It's everywhere in the outer solar system, coating worlds like Pluto and Europa in gleaming sheets. But on Varuna, it's not just present, it's dominant, making up a staggering chunk of the surface. That wouldn't be strange if Varuna orbited closer to the Sun, where warmer temperatures might explain the abundance. Yet out in the Kuiper Belt's deep freeze, water ice should behave differently, often masked by frosts of nitrogen or methane. The fact that Varuna's surface shouts water ice while whispering everything else suggests its history was unusually quiet. No violent resurfacing events, no geysers spewing fresh material. It's a time capsule of primordial ice, preserved in a way most objects aren't. Then there's the hydrocarbon layer. Methane, ethane, and other carbon-rich molecules litter Varuna's crust, but not in the way scientists expected. On Pluto, methane frost dances across the surface in shifting patterns, while on Makemake it forms bright, reflective patches. Varuna's hydrocarbons, though, seem locked in place, chemically altered into something darker and more stubborn. This points to long-term radiation exposure, billions of years of cosmic rays and solar wind bombarding its surface, breaking simple molecules into complex tar-like tholins. But if that's the case, why don't other similarly ancient objects show the same extreme darkening? That's where the mysteries multiply. One theory suggests Varuna was born in a different neighborhood of the primordial solar system, perhaps closer to the giant planets, where gravitational tugs or warmer temperatures altered its chemistry before flinging it outward. Imagine a snowball rolling through soot before settling in the freezer, its composition forever marked by the journey. Another idea leans on collisions. A glancing blow from a carbon-rich body might have smeared foreign material across Varuna's surface, leaving a stain that never fully blended in. But the most tantalizing possibility is that Varuna's mix is a snapshot of the solar system's infancy. The Kuiper Belt is often called the attic of our cosmic neighborhood, stuffed with leftovers from planet formation. If Varuna's ingredients are pristine, relatively untouched by heat or upheaval, they could tell us what the building blocks of planets really looked like. Water ice that never melted, hydrocarbons that never burned away, a recipe frozen in time. Of course, without a closer look, we're left guessing. Every telescope observation adds another piece, but the full picture stays frustratingly blurry. What's clear, though, is that Varuna isn't just another icy rock. Its surface is a palimpsest of the solar system's earliest days, scribbled with clues we're only beginning to decipher. And that makes it one of the most compelling time machines we've got, if only we know how to read it. Varuna's name isn't just a label, it's a bridge between ancient myth and modern astronomy, hinting at deeper connections that stretch across time and space. The Hindu deity Varuna, one of the oldest gods in recorded history, ruled over the cosmic waters and upheld the laws of the universe, a fitting namesake for a distant world shrouded in ice and mystery. But why did astronomers choose this particular name, and could there be more to the connection than poetic symbolism? The answer lies in the delicate dance of scientific tradition and serendipity that guides how celestial bodies are named, and sometimes the universe seems to whisper its own secrets into the process. When Varuna was discovered in the year 2000, the International Astronomical Union faced a challenge, assigning names to the flood of newfound Kuiper Belt objects without repeating the Greco-Roman pantheon that dominates planetary nomenclature. Hindu and other global mythologies offered a rich alternative, and Varuna's role as a cosmic sovereign, especially his association with water and the celestial order, made it an irresistible choice. But here's where Chinese letter feels almost uncanny. While the name was selected for its cultural resonance, Varuna the world later revealed properties that eerily mirror its mythological counterpart. The god presided over the primordial waters and the dwarf planet. Spectroscopic data suggests its surface is laden with water ice, possibly more so than many of its Kuiper Belt neighbors. It's as if the ancients glimpsed something timeless in the stars, a thread linking their stories to realities we're only now uncovering. The parallels don't stop there. In Hindu cosmology, Varuna wasn't just a water god. He was a keeper of hidden truths, a figure who saw beneath the surface of things. That's a hauntingly apt metaphor for a world that challenges our understanding of the solar system at every turn. Its rapid spin, its shadowy crust, its missing atmosphere, each mystery feels like a layer waiting to be peeled back, a cosmic secret guarded by ice and distance. Even the deity's association with cosmic order takes on new meaning when you consider Varuna's place in the Kuiper Belt, a realm of chaos frozen in time, where remnants of the solar system's birth drift like fragments of an unsolved puzzle. Then there's the broader cultural tapestry. Naming celestial bodies after non-Western deities isn't just about diversity. It's a reminder that the sky has always been a canvas for human imagination, no matter where you stand on Earth. Varuna shares the Kuiper Belt with other Hindu-named worlds like Makemake and Haumea, creating a celestial pantheon that reflects humanity's shared heritage. It's a subtle but powerful shift from the Eurocentric naming conventions of the past, inviting us to see the solar system through a wider lens. Yet the choice of Varuna might also hold a quieter, more personal story. Astronomers often describe naming discoveries as an act of poetry, a way to infuse cold data with warmth and meaning. In Hindu tradition, Varuna's gaze was all-seeing, and today our telescopes echo that vision, probing the depths he once symbolized. Whether by accident or some deeper synchronicity, the name binds ancient wonder to modern discovery, a reminder that the universe's greatest mysteries often resonate across millennia. So the next time you hear Varuna, think beyond the ice and rock. Think of the god who ruled the cosmic waters and the world that now carries his name into the unknown. Varuna's path around the sun is anything but ordinary, a lopsided, tilted loop that sets it apart from most of its Kuiper Belt neighbors. While many distant objects follow relatively flat, circular orbits, Varuna's trajectory arcs high above the solar system's plane at a steep 20-degree angle, then swings wildly closer to the sun before retreating back into the frozen depths. This eccentric dance raises two burning questions. How did it end up on such a bizarre route, and what forces could possibly keep it there? The answers might rewrite our understanding of the solar system's most chaotic era. Start with the orbit's peculiar shape. Most Kuiper Belt objects like Pluto trace out elongated but predictable ellipses. Varuna's path, however, is stretched to extremes, with an eccentricity nearly double Pluto's, meaning its distance from the Sun varies dramatically over its 280 Earth-year orbit. At its closest approach, it ventures almost as near as Pluto, only to later recoil over 4 billion miles away, where the Sun is a mere pinprick of light. Such extremes suggest a history of gravitational interference, as if something massive once grabbed Varuna and flung it off course. That something might be Neptune. The ice giant's gravity is the solar system's ultimate disruptor, capable of hurling objects into strange orbits during close encounters. One leading theory posits that Varuna was born closer to the Sun, perhaps near Neptune's original orbit before the planet's outward migration. A phenomenon called the Nice Model scattered it into the Kuiper Belt. Picture a game of cosmic pinball. As Neptune shifted outward billions of years ago, its gravitational nudges could have catapulted Varuna into its current tilted, stretched path. The math supports this. Varuna's orbit resonates faintly with Neptune's, hinting at an ancient gravitational handshake. But there's a twist. Some simulations show that while Neptune might have set Varuna's initial trajectory, another factor, possibly a now ejected ninth planet, could have amplified its orbital oddities. The hypothetical planet 9, thought to lurk far beyond the Kuiper Belt, is theorized to herd some extreme objects into high-inclination orbits. If Varuna's path aligns with these predictions, it might be circumstantial evidence for the missing planet's existence. Or consider another possibility. Varuna could be an interloper. Its chemical makeup and orbit bear striking similarities to the so-called detached objects, a rare class of Kuiper Belt denizens with orbits untethered from Neptune's influence. These outliers, like Sedna, might have been stolen from another star during the Sun's infancy, when our solar system was still nestled in its stellar nursery. If Varuna shares this origin, it's not just odd, it's alien, a relic from another cosmic family tree. What's clear is that Varuna's orbit isn't just a curiosity, it's a fossil record of the solar system's turbulent youth. Every tilt and twist in its path whispers secrets about planetary migrations, lost worlds, and gravitational battles fought billions of years ago. And until we map more of these distant wanderers, Varuna's peculiar journey will remain one of the Kuiper Belt's most tantalizing puzzles. Varuna's loneliness is as striking as its other oddities. It floats through the Kuiper Belt without a single known moon in tow. This is downright strange when you consider its peers. Pluto boasts 5 moons, Haumea has 2 fast-orbiting companions, and even smaller Kuiper Belt objects often sport at least one gravitational partner. So why is Varuna large enough to potentially hold onto satellites seemingly flying solo? The answer could lie in a mix of cosmic accidents, hidden histories, or even the brutal physics of the early solar system. First, let's talk size and gravity. Varuna's diameter, estimated at around 700 kilometers, should theoretically allow it to capture or hold onto moons, especially in the sparsely populated Kuiper Belt where collisions and close encounters are rare. Yet every search from ground-based telescopes to Hubble's sharp eye has come up empty. This suggests one of two scenarios: either Varuna never had moons to begin with, or it lost them catastrophically. The latter possibility is intriguing. Imagine a colossal impact like the one thought to have birthed Pluto's largest moon, Charon. If Varuna suffered a similar collision, the debris might have escaped entirely, flung into interstellar space by its rapid rotation. That spin, clocking in at under 6 hours, could have made it impossible for ejected material to coalesce into stable orbits, leaving the planetoid forever alone. Then there's the environment of its birth. The Kuiper Belt wasn't always the quiet backwater it is today. Billions of years ago, it was a demolition derby of icy bodies, with orbits scrambled by Neptune's outward migration. In that chaos, moons were both created and destroyed. Smaller objects might have been stripped away by passing giants, or nudged into orbits so wide they're virtually undetectable from Earth. For example, Haumea's moons orbit so close they're nearly grazing its surface, while Pluto's farthest moon, Hydra, dances over 60,000 kilometers away. If Varuna's hypothetical moons were ejected or drifted too far, our current telescopes might simply miss them in the glare of their parent body. But the absence of moons might not be a fluke. It could be baked into Varuna's origins. Some planetary scientists argue that not all large Kuiper Belt objects form under the same conditions. While Pluto and Haumea may have coalesced in regions dense with debris, ripe for moon formation, Varuna could have emerged in a sparser pocket of the primordial disk. Without enough material nearby to clump into satellites, it would have stayed solitary from the start. This would also explain its unusually pristine water ice crust. No moons means no tidal heating, no geologic activity to refresh its surface over eons. There's also the tantalizing possibility that we're looking in the wrong way. Varuna's darkness and distance make it a nightmare to observe in detail. Current technology struggles to spot small, dim moons against the blackness of the Kuiper Belt, especially if they're close in or made of the same shadowy material as Varuna itself. Even Pluto's tiniest moons weren't discovered until the New Horizons fly. I revealed them in stunning detail. A future mission to Varuna might uncover a moonlet hiding in its glare, or confirm its status as a true cosmic hermit. Ultimately, Varuna's moonless existence forces us to rethink what we know about how planetary systems form. Is it a victim of chaos, a relic of scarcity, or just hiding its secrets too well? Until we get a closer look, its solitude remains one of the quietest and most profound mysteries in the outer solar system. Varuna's surface isn't just dark, it's unevenly dark with patches that reflect sunlight in bafflingly different ways. This patchwork of light and shadow, known as albedo variation, is like a cosmic fingerprint revealing secrets about the world's history that no other feature can. While most distant objects show some surface irregularities, Varuna's contrasts are unusually pronounced, suggesting a story of violence, change, or even hidden activity beneath its frozen crust. What could cause such stark differences on a world so cold and distant? The clues might lie in a combination of ancient impacts, chemical quirks, and forces we're only beginning to understand. Start with the most obvious explanation: impacts. The Kuiper Belt is a shooting gallery of icy debris, and Varuna's surface has likely weathered countless collisions over billions of years. A particularly large strike could have blasted away darker surface material, exposing brighter subsurface ice beneath. Think of it like scraping away the top layer of old paint to reveal a fresher coat underneath. But here's the wrinkle: impact scars tend to form distinct craters, and Varuna's albedo variations don't always match the expected patterns. Some bright patches sprawl irregularly, as if the material was smeared or spread by some secondary process. That raises the possibility of cryovolcanism, a phenomenon where icy worlds erupt slushy mixtures of water, ammonia, or methane instead of molten rock. While there's no direct evidence of such activity on Varuna yet, the idea isn't far-fetched. Pluto's towering ice mountains and smooth plains prove that even distant worlds can have geologic surprises. Then there's the chemistry angle. Varuna's dark regions are likely rich in tholins, those complex organic molecules forged by eons of radiation. But not all tholins are created equal. Depending on the exact mix of ices and radiation exposure, some areas might have developed thicker or darker coatings than others. Picture a cookie with unevenly distributed chocolate chips. Small differences in ingredient distribution lead to big changes in appearance. Seasonal effects could amplify these contrasts. Though Varuna's seasons are subtle due to its vast distance from the Sun, slight temperature shifts over its 280-year orbit might cause volatile ices like methane to sublimate in some areas and refreeze in others, leaving behind brighter or darker residues. The wild card: internal processes. Even in the frigid Kuiper Belt, heat from radioactive decay or tidal forces can stir sluggish activity beneath the surface. If Varuna's interior is layered, say, with a denser core and a slushy mantle, shifts in mass could occasionally push fresher material upward, creating bright patches amid the darkness. Europa and Enceladus taught us that ice worlds can hide oceans and geysers. While Varuna is unlikely to be that active, it might not be entirely dead either. The most tantalizing takeaway is that these albedo variations aren't just cosmetic. They're a window into Varuna's resilience. A static world would have a uniform surface, but Varuna's patchy glow hints at dynamic forces, whether external or internal, that kept it changing long after the solar system's birth. That makes it more than a fossil. It's a puzzle with pieces still moving, and until we map its surface in detail, every flicker of light and shadow will remain a question waiting for an answer. Varuna's temperature readings are throwing scientists for a loop because this icy world isn't as uniformly frigid as it should be. In the Kuiper Belt, where sunlight is barely a whisper, you'd expect surface temperatures to hover in a predictable deep freeze, somewhere around -230 degrees Celsius. Yet infrared scans reveal odd pockets on Varuna that defy this expectation, with some areas registering noticeably warmer than their surroundings. Not warm by Earth standards, of course, we're talking a difference of just 10 to 15 degrees, but in a place where heat is almost non-existent, even a slight variance is like finding a smoldering ember in a snowbank. What could possibly be causing these thermal quirks? The suspects range from hidden energy sources beneath the ice to cosmic illusions tricking our telescopes. One compelling theory points to Varuna's composition. Darker surfaces, like those stained by tholins, absorb more sunlight, even the feeble rays that reach the Kuiper Belt, while brighter ices reflect them. If Varuna's patchy terrain mixes sooty regions with gleaming water ice, the darker zones could theoretically trap tiny amounts of heat, creating microclimates. It's the same principle behind asphalt heating up on a cold but sunny day. Color matters, but here's the snag. Varuna's orbit keeps it so far from the Sun that solar heating should be negligible. Even over billions of years, the energy difference from albedo variations might not account for the anomalies we're seeing. That suggests something else is at play. Perhaps heat bubbling up from within. Internal warmth isn't as far-fetched as it sounds. Many icy worlds, from Jupiter's moon Europa to Saturn's Enceladus, hide subsurface heat generated by radioactive decay or gravitational squeezing. If Varuna's core contains even a trace of radioactive elements like potassium or uranium, their slow decay could leak warmth through the crust, creating localized hotspots. Alternatively, its rapid spin might generate tidal forces, especially if it once had a moon whose gravitational tug stretched and flexed its interior. While Varuna's solo status makes this less likely, remnants of a long-lost satellite could have left behind a thermal fingerprint. Even residual heat from its violent formation, trapped under insulating layers of ice, might still be escaping in whispers. Then there's the specter of observational error. Measuring temperatures from Earth is like trying to read a thermometer through a fogged-up window. Varuna's distance and dimness force astronomers to rely on indirect methods, like analyzing the infrared light it emits. If darker areas emit less detectable radiation, our instruments might misinterpret their true thermal state. Atmospheric interference, telescope limitations, or even the angle at which Varuna presents itself could skew readings. Compare it to judging a campfire's heat by the glow of its embers. You'll get close but never perfect. New Horizons' flyby of Pluto revealed how wrong Earth-based estimates can be. Until a probe visits Varuna, we're left guessing. Yet the most tantalizing possibility is that these anomalies hint at active processes. On Pluto, nitrogen glaciers flow and mountains of water ice rise, proof that even distant worlds aren't static. If Varuna's warm spots mark vents or volcanoes, however feeble, they'd revolutionize our understanding of Kuiper Belt geology. Or consider seasonal changes. Over centuries, subtle shifts in Varuna's tilt could expose buried ices to minimal sunlight, triggering temporary thaws. The truth might lie in a mix of all these factors, a cosmic cocktail of chemistry, leftover heat, and measurement quirks. Whatever the cause, Varuna's temperature puzzles remind us that the outer solar system is anything but dead. Beneath the frozen crusts of these worlds, energy lingers, waiting to be understood. And until we crack the code, every anomalous degree is a breadcrumb leading deeper into the dark. Beneath Varuna's frozen crust, a tantalizing possibility lurks, one that could rewrite our understanding of the Kuiper Belt's potential for life. Could this distant, dark world hide a subsurface ocean, liquid and vast, sealed under miles of ice? It's not as far-fetched as it sounds. Across the solar system, moons like Europa and Enceladus have taught us that liquid water doesn't need sunlight to thrive, just the right mix of heat, pressure, and chemistry. Varuna, with its odd thermal anomalies and hints of internal activity, might just fit the bill. Start with the ingredients. Europa's ocean exists because Jupiter's relentless gravity stretches and squeezes the moon, generating enough friction to melt ice deep below. Enceladus, smaller but equally dramatic, owes its geysers to Saturn's tidal forces and a rocky core rich in radioactive elements. Varuna lacks a giant planet nearby to tug on it, but it's not without potential heat sources. Its rapid spin could generate internal friction, especially if its interior is layered like a cosmic onion, dense rock at the core, slushy ice above, and a brittle crust on top. Radioactive decay in its core, if present, might provide just enough warmth to keep pockets of water liquid. Even the slight heat from its formation, trapped over billions of years, could contribute. The math is delicate but not impossible. Models of similarly sized icy worlds suggest that under the right conditions, an ocean could persist. Then there's the chemistry. Water alone isn't enough for an ocean to last. It needs antifreeze. On Europa and Enceladus, salts and ammonia lower the freezing point of water, preventing it from solidifying. Varuna's surface spectra hint at complex organics and possibly ammonia hydrates, exactly the kind of compounds that could keep water liquid at ultra-low temperatures. Picture a briny sludge, thicker than Earth's oceans but fluid enough to swirl beneath the ice, perhaps even hosting hydrothermal vents like those thought to nourish alien microbes on our own seafloor. But how would we know for sure? Scientists hunt for subsurface oceans in three key ways. First, surface features, cracks, ridges, or smooth plains hinting at resurfacing by liquid seeping up. Varuna's patchy brightness variations could be scars from such activity, though they're too dim to confirm. Second, magnetic fields. Europa's ocean interacts with Jupiter's magnetism, creating detectable signals. Without a nearby planet's field, Varuna would need its own dynamo, unlikely but not ruled out. The third and most telling clue, plumes. Enceladus famously spews its ocean into space, and Europa may do the same. If Varuna's ocean is under pressure, occasional cryovolcanic eruptions might eject material into orbit, where future telescopes could sniff it for water vapor or salts. The wild card here is time. Even if Varuna once had an ocean, could it still cling to it today? Tidal heating fades as orbits stabilize and radioactive elements decay. But ice is a superb insulator. Some models suggest oceans on dwarf planets could endure for billions of years, especially if laced with antifreeze compounds. Varuna's ocean, if it exists, might be a shadow of its former self, a shrinking, hypersaline sea, its last droplets clinging to hydrothermal vents in the dark. Or it could be young, temporarily thawed by a recent collision or shifting chemistry. The implications are staggering. Life as we know it needs liquid water, and Varuna's potential ocean, however alien, would place it on the shortlist of habitable worlds. Not with forests or fish, perhaps, but with extremophiles thriving in the abyss as they do beneath Earth's ice sheets. More fundamentally, it would prove that oceans aren't unique to the inner solar system or moons of gas giants. They could be hidden everywhere, even in the frozen fringes where we least expect them. Until a probe arrives, Varuna's secrets will stay locked under ice. But every odd temperature reading, every unexplained surface feature, whispers the same tantalizing question: what if? What if, in the endless night of the Kuiper Belt, one of our solar system's strangest worlds is also one of its wettest? Varuna's surface is missing something crucial: scars. In a solar system where ancient worlds are pockmarked with craters from billions of years of bombardment, this distant ice ball stands out for its eerie smoothness. While most Kuiper Belt objects wear their violent histories like badges, think of Pluto's battered plains or Haumea's impact-riddled face, Varuna's terrain seems almost untouched. How could a world this old, drifting in a region crammed with icy debris, evade the cosmic collisions that mark its neighbors? The answer might rewrite what we know about geological activity in the coldest reaches of space. Start with the simplest explanation. Varuna hasn't been around as long as we think. If it's a younger object, perhaps a fragment from a larger body that shattered relatively recently, its surface wouldn't have had time to accumulate the craters seen on older worlds. But that's a tough sell. The Kuiper Belt's era of cataclysmic collisions mostly ended billions of years ago, and Varuna's orbit suggests it's been around since the solar system's infancy. Unless it's a rare outlier, something else must be erasing its scars. Enter resurfacing, the process that renews a world's exterior, burying old craters under fresh material. On active bodies like Europa or Enceladus, liquid water or slushy ice gushes up through cracks, smoothing the terrain. Varuna is too cold for liquid water, but other forces could be at work. One possibility: cryovolcanoes spewing a slurry of ammonia, methane, or nitrogen ice. These exotic eruptions wouldn't look like Earth's fiery volcanoes. Imagine more of a slow, frigid ooze spreading across the surface like pancake batter over a griddle. Over time, that ooze could mask older craters, leaving behind a deceptively youthful face. Or consider seasonal frost migration. Pluto's surface shifts over centuries as nitrogen ice sublimates in sunlight and recondenses in shadow. Varuna's orbit is far more stable, but even subtle temperature changes could cause volatile ices to creep across its terrain, filling in depressions over millennia. Picture a self-healing sidewalk where cracks gradually vanish under layers of fresh frost, except on a planetary scale. Yet another theory points to Varuna's dark, tholin-rich crust. These complex organics, baked by radiation, might form a flexible, tar-like layer that slowly heals impacts. When a crater forms, the dark material could flow back into the depression, like memory foam regaining its shape. This wouldn't erase large craters entirely, but it could soften their edges over time, making them harder to spot from Earth. Then there's the observational elephant in the room. Maybe the craters are there, we just can't see them. Varuna's distance and dimness push telescope resolution to its limits. What looks like a smooth surface from here might be riddled with small, shallow craters obscured by shadows or surface roughness. Even New Horizons images of Pluto revealed far more detail than Earth-based observations ever could. Without a close-up view, we're essentially squinting at a snowman through a blizzard. The most tantalizing takeaway, Varuna's smoothness might not be a single mystery but a cocktail of factors. A dash of cryovolcanism, a sprinkle of frost migration, a pinch of observational limits. Or perhaps something entirely unexpected, a geological process unique to the Kuiper Belt's mid-sized worlds, one we've yet to discover. Whatever the truth, this icy enigma is proof that even in the solar system's quietest corners, nothing stays frozen in time forever. Varuna's peculiar orbit doesn't just defy expectations, it might be whispering secrets about one of astronomy's most tantalizing mysteries, the hypothetical planet 9. Nestled in the Kuiper Belt's outer fringes, Varuna's stretched, tilted path shares eerie similarities with other extreme objects like Sedna and 2015 TG387, all of which seem to cluster in ways that can't be explained by Neptune's gravity alone. This cosmic coincidence has led scientists to wonder, could Varuna's strange dance be choreographed by an unseen giant lurking in the solar system's darkest corners? The Planet 9 theory emerged because certain Kuiper Belt objects don't just orbit randomly, their paths align, as if nudged by something massive. Picture a group of marbles rolling around a table, then suddenly veering toward one edge. Without seeing the tilt, you'd suspect a hidden magnet. Similarly, Varuna's high orbital inclination and elongated trajectory fit simulations where a distant planet, roughly 10 times Earth's mass, tugs these objects into odd configurations over billions of years. The math is compelling. When astronomers model Planet 9's gravitational influence, it neatly explains why Varuna and its kin orbit at such steep angles while most Kuiper Belt objects stay near the solar system's flat plane. But not all clues point the same way. Varuna's orbit isn't as extreme as Sedna's, which loops far beyond the Kuiper Belt into the icy realm of the Oort cloud. This middling oddity raises questions. If Planet 9's pull is strong enough to shepherd Sedna, why hasn't Varuna been yanked into an even wilder path? Some researchers argue Varuna might be a transitional object, one that felt Planet 9's influence but wasn't fully captured by it. Think of it as a comet grazing Jupiter's gravity well, altered but not flung into the abyss. Others propose Varuna's orbit could be a fossil of an earlier, more chaotic solar system, when Neptune's migration sent shockwaves through the Kuiper Belt long before Planet 9's alleged reign began. Then there's the skeptic's take. Not everyone believes Planet 9 exists. Some argue that observational biases could make these odd orbits seem clustered when they're actually random. Varuna might simply be a statistical fluke, its path shaped by ancient collisions or interactions with passing stars during the sun's infancy. After all, the outer solar system is a graveyard of disrupted orbits, and Neptune's gravitational stirrings alone could account for some of the chaos. Yet the intrigue deepens when you compare Varuna to other Planet 9 suspects. Its orbital plane tilts in the same general direction as Sedna's, and its perihelion, the closest point to the Sun, aligns loosely with the predicted cluster. These subtle harmonies keep the theory alive, even as alternative explanations emerge. For example, recent studies suggest a swarm of smaller rogue planets, rather than a single giant, could collectively shepherd these odd orbits. Or perhaps dark matter's gravitational whispers play a role, though that's venturing into speculative territory. The stakes here are cosmic. If Varuna's orbit truly is a signpost for Planet 9, it could lead us to the first new planet discovered in over a century, one that might redefine our solar system's boundaries. Conversely, if Varuna's path has mundane origins, it forces us to rethink how the Kuiper Belt evolved without invoking unseen giants. every new observation, from refined orbital calculations to upcoming telescopes like the Vera Rubin Observatory, brings us closer to an answer. For now, Varuna remains a celestial breadcrumb, hinting at possibilities we can't yet confirm. Whether it's tracing the hand of a hidden planet or simply dancing to the tune of ancient chaos, its orbit is a reminder that the solar system's farthest reaches are still a frontier, and every mystery we uncover there reshapes the story of home. Varuna's age should be a straightforward calculation after all. The solar system's birth is pegged at around 4.5 billion years ago, and most Kuiper Belt objects are assumed to be leftovers from that era. But scratch the surface and the numbers start to unravel. Some estimates place Varuna among the oldest relics of the solar system, while others suggest it might be a relative newcomer, reshuffled into place long after the planets formed. This discrepancy isn't just academic. It's a window into the chaos of the solar system's youth, and whether Varuna witnessed that turmoil firsthand or arrived late to the party could reshape our understanding of how the outer reaches evolved. The case for Varuna as an ancient fossil hinges on its composition. That dark, tholin-rich crust and the abundance of water ice point to prolonged exposure to cosmic radiation, a process that takes billions of years to leave such stark chemical fingerprints. If Varuna had formed closer to the Sun, where temperatures might have stripped away these volatiles, its surface wouldn't look the way it does. Add to that its irregular shape, which hints at a quiet existence away from major collisions, and you've got a convincing argument for a primordial origin. Picture a time capsule frozen in the Kuiper Belt's depths, its surface practically unchanged since the era when Neptune was still carving its path through the debris. But there's a wrinkle: Varuna's orbit. That steep tilt and wild elongation don't match the sedate, circular paths typical of objects that formed in place. Instead, they scream disruption like a billiard ball knocked sideways by a powerful cue. This is where the late arrival theory gains traction. Dynamic models of the early solar system suggest that as Neptune migrated outward, its gravity sent shockwaves through the Kuiper Belt, flinging objects like Varuna into their current eccentric orbits. If that's true, Varuna might have originated much closer to the Sun, possibly in the same region as Pluto before being hurled into the deep freeze. Its surface, then, could be a palimpsest of two histories: an initial formation in a warmer, busier part of the solar system, followed by billions of years of radiation baking in the Kuiper Belt. The debate gets even murkier when you consider Varuna's family, or lack thereof. Most ancient Kuiper Belt objects belong to dynamical families, groups with similar orbits tracing back to a single shattered parent body. Varuna, though, orbits in isolation. That could mean it's a lone survivor of a long-gone population, or that it's an interloper from another part of the solar system entirely. Some simulations even suggest it might be a captured object, stolen from another star during the Sun's infancy when stellar nurseries were crowded with sibling stars. If so, its age might not align with the solar system's timeline at all. Unraveling this mystery isn't just about pinning a number on Varuna, it's about testing our models of solar system formation. If Varuna is ancient and local, it implies the Kuiper Belt structure was set early and remained stable. If it's a scattered refugee, that paints a picture of a violent, reshuffling outer solar system. And if it's truly alien, that opens the door to a solar system stitched together from stolen fragments, a cosmic collage of borrowed worlds. Until we can sample its surface or track its orbit with pinpoint precision, Varuna's age will remain one of its most tantalizing puzzles, a riddle written in ice and time. Varuna's brightness has a mind of its own, flickering unpredictably like a candle in the cosmic wind. For an object so far from the Sun, where light is scarce and change is slow, these erratic shifts in luminosity are baffling. One month, telescopes catch it glowing faintly, the next it's inexplicably brighter. What could cause such capricious behavior on a world we'd expect to be as steady as a frozen clock? The answer might lie in a tug of war between its chaotic spin, a surface in flux, and the invisible hand of deep space radiation. First, consider rotation. Most planets and dwarf planets spin with reassuring regularity, their brightness varying only as different hemispheres turn toward Earth. Varuna, however, whirls so fast and possibly so unevenly that its shape could be warped like a tumbling potato rather than a perfect sphere. If its elongated form twists as it spins, presenting wider or narrower faces to our telescopes, that alone could explain some brightness shifts. But there's a catch. Varuna's fluctuations don't always sync up with its rotation period. Some changes occur too abruptly, as if something on its surface is altering in real time. That something might be its dark, volatile crust. Picture a landscape where patches of superdark tholins lie next to gleaming water ice. Over time, solar radiation, even the feeble amount this far out, could vaporize trace chemicals like methane or nitrogen, leaving brighter ices exposed. Conversely, fresh impacts or cryovolcanic oozes might dredge up darker material, dimming whole regions like ink spilled on snow. On Pluto, similar processes create climate cycles lasting centuries. Varuna's changes are faster and more erratic, suggesting its surface chemistry is uniquely unstable. Then there's the wild card, space weather. The Kuiper Belt isn't the serene graveyard we once imagined. Cosmic rays and solar wind particles, though sparse, constantly bombard objects like Varuna, charging their surfaces with static electricity or triggering chemical reactions. A single high-energy burst could zap its crust, temporarily altering how light reflects off it. Imagine stepping outside on a foggy night, the way street lamps seem brighter or dimmer as the mist thickens or thins. Varuna might be experiencing its own version of this, with cosmic rays acting as the unseen fog. The most tantalizing possibility, Varuna's brightness changes could be a symptom of something deeper, literally. If it harbors a subsurface ocean, as some theories suggest, occasional geysers or plume activity might eject fresh ice crystals into space, creating a fleeting halo that boosts its reflectivity. Europa and Enceladus do this routinely, though their plumes are powered by nearby gas giants. Without such a gravitational powerhouse, Varuna's outbursts would be fainter and rarer, but not impossible. For now, every flicker in Varuna's glow is a breadcrumb leading toward larger truths. Whether it's the convulsions of a world refusing to stay still, the scars of an environment more dynamic than we dreamed, or whispers of hidden oceans, one thing's clear: this icy enigma won't be pinned down easily. And that's precisely what makes it worth watching. Varuna's density is a cosmic contradiction, a puzzle that defies the basic rules we've come to expect from Kuiper Belt objects. For a body its size, roughly half the diameter of Pluto, scientists predicted a density close to that of water ice, around 1 gram per cubic centimeter. But the numbers tell a different story. Measurements suggest Varuna's density might be as low as 0.7 grams per cubic centimeter, or as high as 1.3, depending on the model. That's the difference between a world lighter than a block of wood and one denser than most icy moons. What could explain such wild inconsistencies? The answer might lie in a hidden core, a hollowed-out interior, or forces we've yet to fully understand. Start with the lower end of the spectrum. A density below water ice suggests Varuna isn't just an icy rock. It's more like a frozen sponge riddled with empty spaces inside. This isn't unheard of in the outer solar system. Many smaller Kuiper Belt objects are rubble piles, loose collections of ice and dust held together by gravity, with gaps between chunks making them far less dense than they appear. But Varuna's size complicates this. Gravity usually compresses larger objects, squeezing out voids over time. For something as substantial as Varuna to stay porous after billions of years, its structure would need to be remarkably rigid, resisting collapse like a celestial igloo. Some scientists point to its rapid spin as a possible culprit. Centrifugal force might be counteracting gravity, preventing compaction. Yet even that explanation feels incomplete. Other fast-spinning objects like Haumea don't show such extreme fluffiness. Then there's the higher density scenario. If Varuna clocks in closer to 1.3 grams per cubic centimeter, it hints at something unexpected lurking beneath the ice rock. Most Kuiper Belt objects are thought to be icy through and through, but a rocky core would explain the extra heft. The trouble is, rock-heavy bodies usually form closer to the sun, where temperatures allowed silicates to condense. If Varuna has a significant rocky component, it might mean it originated in the inner solar system before being flung outward during Neptune's migration. Picture a cosmic game of pinball, where a world born near Mars ends up in the Kuiper Belt's deep freeze. Alternatively, Varuna could be the remnant of a once larger body that collided with another rock-rich object, leaving behind a hybrid of ice and stone. The wildest possibility, Varuna's density isn't constant at all. Some models suggest its interior could be layered, with pockets of compressed ice near the core and more porous material near the surface. This would make it less like a uniform snowball and more like a frozen soufflé with inconsistent density throughout. On Earth, we see something similar in glaciers, where ice can contain trapped air bubbles or denser, older layers. If Varuna's interior has undergone partial melting and refreezing, perhaps due to radioactive decay or tidal heating, its density could vary dramatically from crust to core. The implications stretch far beyond Varuna itself. If it's porous, it challenges our assumptions about how mid-sized icy worlds evolve. If it's rock-laden, it hints at a solar system where planetary building blocks were violently shuffled like a deck of cards. And if its density is uneven, that opens the door to a new class of patchwork worlds, each with its own chaotic internal story. Until we send a probe to peer beneath its icy shell, Varuna's density will remain one of its most stubborn mysteries, a reminder that even the simplest measurements can upend everything we think we know. Varuna might not be alone after all. Whispers in astronomical circles suggest this enigmatic world could have a tiny companion, a silent partner in its cosmic dance. The evidence is faint and unconfirmed but tantalizing. Occasional dips in brightness that don't quite match Varuna's rotation, or subtle wobbles in its position that hint at gravitational tugs from an unseen neighbor. If true, this would catapult Varuna into an elite club of binary Kuiper Belt objects, joining the likes of Pluto and its moon Charon. But detecting such a partner isn't just challenging, it's like trying to spot a flickering candle next to a bonfire from thousands of miles away. The Kuiper Belt is a notoriously difficult place to spot small, dim objects. Varuna's distance means even Hubble struggles to resolve details finer than a few pixels, and any potential moon would likely be lost in the glare of its parent body. Add to that Varuna's own rapid spin and irregular shape, which can mimic the brightness variations a moon might cause, and the signal becomes even murkier. Most binary Kuiper Belt objects were discovered through painstaking analysis of light curves or direct imaging during rare, favorable alignments. For Varuna, the data remains frustratingly ambiguous, a flicker here, a blip there, but nothing definitive enough to declare a discovery. Yet the implications of a binary Varuna would be profound. Moons in the Kuiper Belt aren't just decorative, they're time capsules. The way they orbit, their size ratios, and even their compositions can reveal how these distant worlds formed. Take Pluto and Charon. Their tight, synchronized dance suggests a violent collision billions of years ago, a catastrophic impact that birthed a system of moons. If Varuna has a companion, it might tell a similar story, one of chaos in the early solar system, where collisions were the rule rather than the exception. Alternatively, a small moon could be a captured object, a wanderer snared by Varuna's gravity, hinting at a more sedate history of gentle gravitational encounters. The size of the hypothetical moon matters too. A large companion like Charon relative to Pluto would imply a dramatic past, perhaps a shattering impact that left Varuna with its odd shape and rapid spin. A smaller moon, though, might suggest a quieter history where debris from minor collisions coalesced into a modest partner. Even the moon's orbit would be revealing, circular and close in, like Pluto's inner moons, or wide and elliptical, like Nix and Hydra. Each scenario paints a different picture of Varuna's origins and evolution. Then there's the wildest possibility. What if Varuna's companion isn't a moon at all, but a twin? Some Kuiper Belt binaries, like Patroclus and Menoetius, are nearly equal in size, orbiting a shared center of gravity. These pairs are thought to be primordial, dating back to the solar system's birth. If Varuna is part of such a duo, it would challenge our assumptions about how mid-sized Kuiper Belt objects form, suggesting they might have budded off from larger parent bodies or emerged as pairs from the spinning disk of debris that birthed the planets. For now, the question of Varuna's binary nature remains open. New telescopes like the upcoming Vera Rubin Observatory could finally settle the debate with their unprecedented sensitivity. But whether Varuna travels solo or with a companion, the search itself is a reminder of how much we still don't know about the solar system's farthest frontiers. Every flicker of light, every wobble in position is a clue waiting to be deciphered, and the answers could rewrite the story of the Kuiper Belt. Varuna's surface isn't just a monochrome slab of ice, it's a cosmic chameleon, shifting colors depending on who's looking. Telescopes around the world have reported wildly different hues, from dull reds to muted grays, with no clear consensus on which shade is the real Varuna. At first glance, this seems like a trivial discrepancy, but the implications are anything but. These inconsistencies might reveal fundamental truths about the object's composition, or they could expose the limits of our technology in probing the solar system's darkest corners. Start with the instruments themselves. Observing distant Kuiper Belt objects is like trying to identify a painting through a keyhole. Every telescope offers only a sliver of the full picture. Ground-based telescopes, for instance, must peer through Earth's turbulent atmosphere, which scatters and distorts light, subtly altering the colors they detect. Space telescopes like Hubble avoid this problem but face their own challenges. Varuna's extreme distance means even its reflected light arrives as a feeble whisper, forcing astronomers to amplify signals in ways that can unintentionally skew color data. Add to this the quirks of different camera filters and calibration techniques, and it's no wonder telescopes disagree. One might emphasize reddish tholins in its spectra, while another highlights bluer water ice, creating a patchwork of interpretations. But what if the discrepancies aren't just artifacts of observation? Varuna's surface could genuinely host a kaleidoscope of materials, each reflecting light differently depending on the angle of view. Picture a weathered highway at night. Asphalt appears black under direct light but glows silvery when struck at a glancing angle. Varuna's rapid spin means telescopes catch it at varying orientations, potentially revealing different surface patches with distinct compositions. Some areas might be rich in pristine water ice, scattering light in cooler tones, while others are coated in reddish-brown tholins, absorbing shorter wavelengths. Even minor variations in texture, say a patch of coarse, porous ice next to a smooth, glassy plain, could dramatically alter how light bounces off, fooling distant observers into seeing phantom color shifts. The wildest possibility, Varuna's surface might be actively changing. On Pluto, seasonal shifts cause nitrogen frosts to migrate, brightening some regions while others darken. While Varuna's orbit is more stable, its dark, radiation-baked crust could still undergo subtle transformations. Solar wind or cosmic rays might bleach certain compounds over time, while micrometeorite impacts expose fresh ice beneath. If different telescopes observe Varuna years apart, they could literally be seeing different versions of its surface, like photographing a forest in summer and winter. The stakes here are higher than they appear. Color isn't just aesthetics, it's a direct window into chemistry and history. If Varuna's palette fluctuates due to active processes, it joins an elite club of living worlds like Io or Triton, where surfaces renew themselves in real time. If the variations are observational, they underscore the need for better tools like NASA's upcoming James Webb Space Telescope, which could cut through the noise with infrared precision. Either way, this chromatic mystery reminds us that the outer solar system is anything but static. It's a dynamic, evolving frontier where even the simplest observations can upend expectations. Varuna's silent dance with the solar wind paints a portrait of resilience or perhaps quiet surrender. Unlike Earth, shielded by its robust magnetic field and thick atmosphere, this distant Kuiper Belt object faces the sun's relentless particle barrage with almost no defenses. The solar wind, a stream of charged particles racing outward at millions of kilometers per hour, should, in theory, strip Varuna's surface bare over time, scouring away volatile ices and leaving behind a barren wasteland. Yet somehow Varuna persists, its dark crust and patchy brightness variations hinting at a far more complex relationship with these invisible forces. Could this invisible erosion hold the key to its most puzzling features? First, consider the basics. Without an atmosphere to absorb or deflect the solar wind, charged particles slam directly into Varuna's surface, knocking atoms loose in a process called sputtering. On airless bodies like the Moon, this creates the iconic space weathering that darkens lunar regolith over time. But Varuna's surface is already eerily dark, darker than most weathered objects in the solar system. This suggests something unusual is at play. Either the solar wind's effects are amplified here, creating ultra-dark tholins at an accelerated rate, or another process like cryovolcanism is continuously refreshing parts of the surface, creating a tug-of-war between darkening and renewal. The unevenness of this weathering might explain Varuna's patchy albedo. Solar wind doesn't strike evenly. It follows magnetic field lines and can be funneled by an object's rotation or local topography. If Varuna's rapid spin exposes certain regions to more prolonged bombardment, those areas could darken faster, leaving others relatively bright. Imagine a rotisserie chicken browning unevenly over a flame, except here the flame is a torrent of high-energy particles and the chicken is a primordial ice ball. This could account for the strange brightness variations that telescopes struggle to interpret. Then there's the wild card, transient emissions. On more active worlds like Jupiter's moon Io, solar wind interactions generate detectable radio waves or auroras. Varuna lacks the volcanic activity or magnetic field to produce such dramatic displays, but subtle interactions could still occur. Some models suggest that when solar wind ions collide with surface ices, they might release faint ultraviolet glows or even trigger short-lived bursts of ionized gas. These emissions would be vanishingly faint far below current detection limits, but future missions equipped with sensitive plasma detectors might catch whispers of this silent dialogue. The most tantalizing possibility, solar wind could be sculpting Varuna's chemistry in ways we've barely imagined. Laboratory experiments show that proton bombardment, a proxy for solar wind, can transform simple methane ice into complex hydrocarbons, the building blocks of tholins. If this process dominates Varuna's surface evolution, it would mean the solar wind isn't just weathering the world, it's actively rewriting its chemical identity, molecule by molecule. Over billions of years, this could turn Varuna into a refinery for organic compounds, a factory for the very materials that might seed life elsewhere. Yet for all its destructive potential, the solar wind might also be Varuna's unlikely architect. Without it, the world's surface might be uniformly bright, its mysteries buried under pristine ice. Instead, this relentless particle stream has etched a story into the ice one we're only beginning to decode. Every dark patch, every odd reflection, could be a syllable in a narrative written by the sun itself. And until we listen closely, Varuna's silent conversation with the solar wind will remain one of its most profound and least understood exchanges. Varuna's chemistry presents a striking absence. It should be rich in volatile compounds like methane, nitrogen, or carbon monoxide, yet these materials are conspicuously missing from its spectral fingerprints. This isn't just a minor discrepancy, it's a glaring gap in our understanding of Kuiper Belt composition. Everywhere else in the outer solar system, from Pluto's frosty plains to Triton's geysers, volatiles are the rule. So why does Varuna, an object large enough to hold onto such materials, seem to defy expectations? The answer might involve a cosmic vanishing act, a primordial quirk, or forces we've yet to account for. Start with the simplest explanation. Varuna never had volatiles to begin with. While counterintuitive, this isn't impossible. The Kuiper Belt is a diverse place with objects forming under different conditions. If Varuna coalesced in a region where nitrogen or methane was scarce, perhaps near the edge of the solar nebula where temperatures prevented these ices from condensing, its composition would reflect that scarcity. Picture a desert world compared to a tropical one, same planetary neighborhood, radically different ingredients. This would make Varuna a geologic outlier, a relic from a pocket of the early solar system where chemistry took a divergent path. But there's a catch. Varuna's orbit suggests it didn't form in place. It was likely scattered outward by Neptune's migration, meaning it originated closer to the Sun where volatiles were abundant. This raises the possibility of a second scenario. Varuna once harbored these compounds but lost them over time. The process could have been gradual, like a slow leak. On Pluto, methane and nitrogen escape into space but are constantly replenished by sublimating surface ice. Varuna, smaller and less massive, might lack the gravity to retain these gases, bleeding them away until only traces remain. Alternatively, a catastrophic event, like a colossal impact, could have blasted its volatile reserves into space in one violent expulsion. The plot thickens when you consider surface chemistry. Varuna's dark tholin-rich crust hints that some methane was present long enough to be irradiated into complex organics. This suggests volatiles weren't entirely absent, they were transformed. Cosmic rays and solar wind could have broken methane molecules apart, binding carbon into dark tholins while hydrogen escaped into space. Nitrogen, if it ever existed, might have met a similar fate, its lighter atoms drifting away while heavier residues blended into the ice. It's like finding the charred remains of a log in a fireplace. The wood is gone, but the ash tells its story. Then there's the observational blind spot. Detecting volatiles on Varuna isn't easy. Methane and nitrogen ices absorb specific wavelengths of infrared light, but if they're buried under a thick layer of radiation-darkened tholins, our telescopes might miss them entirely. New Horizons' flyby of Pluto revealed vast deposits of methane and nitrogen that Earth-based instruments had underestimated. Varuna could harbor similar hidden reservoirs beneath its inky surface. Or perhaps its volatiles exist in an unusual phase mixed with water ice in clathrates, for instance, which would alter their spectral signatures, the most intriguing possibility. Varuna's volatiles are locked away, not lost. On Saturn's moon Enceladus, gases are trapped beneath an icy shell, erupting sporadically through fissures. If Varuna has a subsurface ocean or slushy mantle, methane or nitrogen could be sequestered there, occasionally venting to the surface but otherwise invisible. This would make Varuna an active world in disguise, its missing volatiles not absent but hiding in plain sight. Ultimately, this mystery isn't just about what's missing, it's about the stories those absences tell. Whether Varuna was born different, stripped bare by time, or quietly hoarding its riches underground, its volatile deficit forces us to rethink the Kuiper Belt's diversity. These icy worlds aren't uniform, they're individuals, each with its own history etched into chemistry and ice. And until we peer closer, Varuna's silence on the matter will keep us guessing. Varuna's true significance might lie not in its oddities alone, but in what it preserves, a frozen window into the solar system's birth. While most planets and moons have been reshaped by heat, collisions, or geological activity over billions of years, this distant world could be a time capsule, its icy crust and peculiar orbit holding untarnished clues about how the building blocks of planets first came together. The key to unlocking this mystery lies in its very strangeness. Varuna's rapid spin, dark surface, and volatile starved composition might not just be random quirks. They could be signatures of conditions in the protoplanetary disk, preserved like fingerprints in ice. Consider the chaos of the early solar system. Before planets took shape, the Sun was encircled by a swirling disk of gas and dust, with temperatures and densities varying wildly at different distances. Close to the Sun, silicates and metals dominated, giving rise to rocky worlds like Earth. Farther out, ices and organics prevailed, eventually forming giants like Neptune and the Kuiper Belt's frozen remnants. Varuna's composition, water ice laced with tholins but lacking abundant methane or nitrogen, suggests it may have formed in a transitional zone, where temperatures were cold enough for water to freeze but too warm for more volatile compounds to condense. This would make it a rare snapshot of a specific moment in the disk's cooling process, capturing a chemical gradient that most other objects have since erased. The surprises don't stop there. Varuna's elongated shape and lack of moons might also be primordial traits. In the disk's earliest stages, before gravity had fully sculpted worlds into spheres, clumps of material could have remained irregular, their growth stunted by the turbulent environment. If Varuna was one of these early planetesimals, it might represent a stalled blueprint, a body that never quite graduated to full planet status. Its isolation supports this. Without the gravitational stirring of larger neighbors, it could have avoided the collisions that rounded out peers like Pluto. Yet the most tantalizing possibility is that Varuna isn't just a relic, it's a refugee. Some models of planetary migration suggest the Kuiper Belt was seeded by objects flung outward from closer to the Sun during Neptune's violent youth. If Varuna was among these migrants, its chemistry and structure could reveal details about the inner solar system's icy fringe, a region now vanished. Imagine finding a washed-up piece of driftwood and using it to reconstruct an entire forest. Varuna's ice might hold similar echoes of lost environments. The stakes for understanding this are cosmic. If Varuna truly is a primordial survivor, studying it could answer fundamental questions. How did ices and organics distribute in the young solar system? What stopped certain objects from growing into planets? Are its oddities the rule for untouched worlds, or the exception? Missions like New Horizons transformed Pluto from a blur into a dynamic world. A similar visit to Varuna could do the same for our grasp of solar system infancy. Until then, every flicker of light, every spectral line, is a whisper from a time before planets, an invitation to decode the universe's quietest archives. Varuna's light curve is a celestial paradox, a rhythmic flicker of brightness that defies every textbook prediction about how an object of its shape and size should behave. Normally, when astronomers observe a rotating, elongated body like Varuna, they expect a smooth, predictable light curve. Brightness peaks as the widest face turns toward Earth, then dips as the narrower sides come into view. But Varuna plays by its own rules. Its light curve wobbles erratically, with unexpected dips and spikes that suggest something far stranger is at work. This isn't just a mismatch between theory and observation. It's a glaring anomaly that could rewrite our understanding of how distant icy worlds evolve. The most straightforward explanation for this oddity would be surface irregularities. Imagine Varuna not as a smooth, stretched oval, but as a cosmic potato, lumpy and asymmetric. A towering mountain range or a deep basin on one side could distort the light curve, creating unexpected brightening or dimming as those features rotate into view. On asteroid Eros, for example, similar irregularities were discovered to cause jagged spikes in its light curve, betraying craters and ridges invisible to telescopes. But Varuna's case is more puzzling. The variations in brightness are too extreme to be explained by topography alone, unless its surface is scarred by structures far more dramatic than anything seen on similar worlds. That's where the second theory comes in, an unseen companion. A moon or even a binary partner could tug gravitationally on Varuna, altering its rotation or casting shadows that disrupt the light curve. The dwarf planet Haumea, with its two rapidly orbiting moons, exhibits similar chaotic brightness patterns, yet searches for a Varunan moon have come up empty, leaving astronomers to wonder if any companion would have to be exceptionally small, dark, or close to the primary body to evade detection. Alternatively, the companion might have already been consumed, a moon that spiraled too close and shattered, leaving behind debris that now orbits invisibly, like a ghostly ring system stirring up turbulence. The wildest possibility is that Varuna's light curve isn't just about shape or companions, it's a sign of something happening beneath the surface. On Earth, we see how shifting tectonic plates or volcanic activity can alter landscapes. What if Varuna's icy shell is similarly dynamic? Cryovolcanic plumes, subsurface landslides, or even seasonal sublimation of ices could expose fresh, reflective patches or buried darker terrain, tweaking the light curve in real time. Europa's ever-changing cracks and Pluto's shifting glaciers prove that ice worlds aren't static, and Varuna's erratic brightness might be the first clue that it, too, refuses to sit still. Then there's the observational wild card, perspective. Varuna's tilt and our viewing angle from Earth might be conspiring to distort the data. If we're seeing it pole on rather than equator on, for instance, its rotation could produce unexpected light variations that defy conventional models. It's like trying to gauge the shape of a spinning top by staring straight down at it. The usual cues vanish, leaving only cryptic hints. The implications stretch far beyond Varuna itself. If its light curve stems from surface activity, it joins an elite club of living worlds where geology refuses to freeze. If a hidden companion is to blame, it suggests moons in the Kuiper Belt are more common and more elusive than we thought. And if the answer lies in some exotic interplay of shape, spin, and shadow, it could mean our models for distant objects need a complete overhaul. Every flicker of Varuna's light is a coded message from the edge of the solar system, and decoding it might just reveal how much we've underestimated the chaos of the cosmic deep freeze. Varuna's status hangs in cosmic limbo. It's large enough to flirt with dwarf planet classification, yet remains officially relegated to the ranks of mere Kuiper Belt objects. Why hasn't this icy world joined Pluto, Eris, and Haumea in the dwarf planet club? The answer lies in a tug of war between scientific criteria and the murky realities of observing distant worlds. The International Astronomical Union lays out 3 non-negotiable rules for dwarf planet status. First, the object must orbit the Sun, check for Varuna. Second, it must have enough mass for gravity to mold it into a near-spherical shape. This is where debates ignite. Varuna's elongated form, revealed by its erratic light curve, suggests gravity hasn't fully smoothed it into hydrostatic equilibrium, the technical term for that round planetary look. But here's the twist: the line between round enough and too lumpy isn't razor-sharp. Haumea, officially a dwarf planet, resembles a squashed football due to its rapid spin, yet it made the cut. Varuna's similar distortion raises questions about whether the IAU standards need nuance for fast-rotating worlds. The third criterion, clearing its orbital neighborhood, is even trickier. Varuna shares the Kuiper Belt with thousands of other objects, failing to dominate its orbital zone like Pluto does. But some astronomers argue this rule unfairly favors objects closer to the Sun, where gravitational influence is easier to assert. In the sparse outer reaches, even massive bodies might never clear their orbits simply because there's less debris to begin with. If the definition were adjusted for regional density, Varuna could suddenly qualify. New data might tip the scales. Recent observations hint at possible cryovolcanic activity or subsurface layers that could imply a more differentiated, planet-like interior. If future missions confirm Varuna has a complex geology, say, a layered structure with a rocky core and icy mantle, it would strengthen the case for its upgrade. The Dawn spacecraft's visit to Ceres transformed it from asteroid to dwarf planet overnight. Varuna could follow suit with closer scrutiny. The stakes are higher than a label. Dwarf planet status unlocks funding for dedicated studies and missions, putting worlds on astronomers' priority lists. For now, Varuna lingers in the shadows, a celestial understudy waiting for its moment in the spotlight. But as our tools improve and definitions evolve, this icy enigma might yet claim its place among the solar system's most intriguing small worlds. Varuna remains one of the solar system's great unexplored frontiers, not because it lacks intrigue, but because no spacecraft has ever ventured close enough to unravel its secrets. For a world that defies so many expectations, this absence of mission data is stark. Pluto, once just a blur in telescopes, became a dynamic, geologically active world under New Horizons' gaze. Yet Varuna, equally mysterious, lingers in the shadows. The reasons for this oversight reveal the harsh realities of deep space exploration, a mix of logistical nightmares, shifting priorities, and the cold calculus of scientific return on investment. First, consider the sheer distance. Varuna orbits the Sun at an average distance of 4 billion miles, nearly 50% farther than Pluto. Sending a probe that far requires monumental energy and time. New Horizons took 9 years to reach Pluto, and a Varuna mission would stretch that timeline well over a decade. Adding to the challenge, Varuna's orbit is wildly elliptical, meaning a spacecraft would need perfect timing to intercept it at its closest approach. Miss that window, and the journey could take decades longer. Compare this to missions like Dawn's visit to Ceres or Juno's orbits around Jupiter, targets closer to Earth with more predictable paths. Every extra year of travel translates to ballooning costs and aging technology, risks funding agencies are reluctant to take. Then there's the question of scientific payoff. Space missions are expensive, and every dollar spent must be justified by potential discoveries. Pluto's atmosphere, glaciers, and mountains made it a high-priority target, while Varuna's darker, quieter profile raises doubts. Without an obvious atmosphere or known geological activity, it's harder to sell as a must-visit destination. Yet this logic overlooks Varuna's subtler allure. Its bizarre rotation, possible subsurface ocean, and primordial surface could answer foundational questions about how mid-sized icy worlds evolve. Is its darkness a veil hiding cryovolcanoes? Does its oblong shape hint at a violent past? These unknowns could revolutionize our understanding of the Kuiper Belt if we're willing to look. Competition from other targets further complicates the picture. The Kuiper Belt teems with objects vying for attention. Haumea with its rings, Arrokoth's pristine binary structure, or Sedna's extreme orbit. Each offers unique scientific value, and spacecraft can't visit them all. Varuna's middle-of-the-pack size and lack of flashy features make it a harder sell, especially when flagship missions like Europa Clipper or Uranus orbiters promise clearer, paradigm-shifting results. It's a cosmic beauty contest, and Varuna's understated mysteries struggle to stand out. Technological barriers add another layer. Communicating with a probe at Varuna's distance demands ultra-sensitive antennas and power-intensive transmitters infrastructure that's already stretched thin, supporting existing missions. The faint sunlight at those ranges also limits solar power, forcing reliance on nuclear batteries like New Horizons plutonium-fueled RTG, with global stockpiles of plutonium-238 dwindling. Every gram is precious, and missions closer to home often take priority. Yet the tide may be turning. Advances in propulsion like NASA upcoming solar sail projects or next-generation ion drives could slash travel times. Miniaturized instruments might allow smaller, cheaper probes to deliver big science, and as astronomers uncover more about Varuna's oddities, its fluctuating brightness, potential moon, or thermal anomalies, the case for a visit grows stronger. The darkest corners of the solar system often hold the brightest surprises, and Varuna's stillness might just be the calm before a storm of discovery. Until then, it remains a puzzle waiting for its solver, a world frozen in more ways than one. Varuna's future is written in the slow, patient hand of cosmic time, a script unfolding over millions, even billions of years. Right now, it spins in the outer darkness, a frozen relic of the solar system's birth, but change is inevitable. The question is, what form will that change take? Will it drift silently into the void, untouched and unchanging, or will forces both subtle and violent reshape it beyond recognition? First, let's talk about its orbit. Varuna's current path is a lopsided loop, tilted and stretched, but gravity is a patient sculptor. Over eons, Neptune's distant tugs could nudge it toward a more circular orbit, steadying its wild swings. Alternatively, if the hypothetical planet 9 exists, its gravitational influence might yank Varuna into an even more extreme trajectory, flinging it deeper into the Kuiper Belt, or even ejecting it entirely. Picture a cosmic game of pinball where Varuna's fate hinges on unseen players, and then there's the chance of a close encounter with another massive object. One stray gravitational handshake could send it careening toward the inner solar system, transforming it from an icy enigma into a long-period comet, its surface erupting in geysers as the sun's warmth finally reaches it. Then there's the matter of its surface. Varuna's dark, tholin-stained crust is already one of the least reflective in the solar system, but radiation isn't done with it yet. Over millions of years, relentless cosmic rays will continue breaking down its ices into ever more complex and darker organic compounds. Its patches of bright water ice, already scarce, might vanish entirely, leaving it a featureless charcoal husk. Or if cryovolcanism stirs beneath its crust, fresh eruptions could repaint the surface in fleeting bursts of brightness, a counterpoint to the deepening darkness. The balance between these two forces, radiation's decay and geology's renewal, will determine whether Varuna becomes a shadow or surprises us with bursts of activity. Collisions are the wild card. The Kuiper Belt may seem empty, but it's a shooting gallery of slow-moving icy bodies. A single impact could shatter Varuna into fragments, scattering a new family of objects in its wake. Alternatively, a gentler merger might bulk it up, adding enough mass to finally round it into a proper sphere and cement its status as a dwarf planet. The odds are slim, but over billions of years, even rare events become inevitable. And what of its spin? That breakneck rotation won't last forever. Tides from a hypothetical moon, or even the sun's weak gravitational pull, could gradually slow it down, stretching its 6-hour day into something more sedate. Or if it's ever captured into a resonant orbit with Neptune, the giant planet's gravity might lock it into a rhythmic dance, much like Pluto's relationship with Charon. But the most profound change could come from within. If Varuna hides a subsurface ocean, the slow cooling of its core might eventually freeze it solid, cracking the crust with ice quakes. Or residual heat could keep that ocean liquid far longer than expected, prolonging the chance for hidden chemistry, or even, against all odds, life. Varuna's future isn't just a passive drift toward entropy. It's a mosaic of possibilities, some slow and silent, others sudden and spectacular. Whether it ends as a darkened fossil, a scattered debris field, or a reshaped world, its story will be a testament to the dynamism of even the coldest corners of the cosmos. And long after humanity is gone, it will keep spinning, evolving, and whispering its secrets to the stars. Varuna stands as one of the solar system's most enigmatic puzzles, a world that refuses to fit neatly into any of our cosmic categories. From its breakneck spin, defying the laws of rotation for an object its size, to its shadowy, uneven surface that seems to shift before our telescope's eyes, every observation raises new questions. Why does this icy relic lack the atmosphere that cloaks its neighbors? What erased the craters that should mark its ancient face? Could its bizarre orbit be a trail of breadcrumbs leading to the hypothetical planet 9? Or is it a survivor of some long-forgotten celestial collision? The mysteries only deepen the closer we look. Then there's the riddle of its missing moons, a solitude that sets it apart from nearly every other large Kuiper Belt object. Is it truly alone, or are we just not seeing its hidden companions? Its fluctuating brightness and strange colors hint at processes we can't yet explain, while its density readings swing wildly between lightweight fluff and rock-heavy heft, leaving us unsure if it's a fragile snowball or a dense time capsule from the solar system's birth. And beneath that cracked, dark crust could an ocean lurk, liquid and secret, defying the cold of deep space. Even its name carries whispers of the uncanny, a Hindu deity of cosmic waters, echoing the very ices we now find on its surface. Is that resonance coincidence or a reminder that the universe often outpaces our imagination? The truth is, after centuries of studying the skies, Varuna proves how much we still don't know. It's a reminder that the cosmos thrives on mysteries, and every answer we uncover only reveals deeper layers of questions. So what's next? Maybe one day, a spacecraft will brave the billions of miles to Varuna, snapping photos that rewrite our textbooks. Until then, it's up to us to keep wondering, theorizing, and peering into the darkness with curiosity. What's your take on Varuna's strangest secrets? Do you think its oddities point to something we've never imagined? Drop your wildest theories in the comments. After all, the best discoveries start with a little audacity. And if you've got a favorite space mystery you'd love us to explore next, let us know. The universe is vast, but the journey to understand it begins with a single question. Keep looking.